Hello there, 6th grade. We're working on week 4. First lesson of this is section 6.2.4. We are going to be wrapping up chapter 6 this week, and then from here on out we're going to move into chapter 7. Just a heads up, we may end up skipping some sections, so keep that in mind, just based off what I want you to cover between now and the end of the school year. So as you can see, I have the assignment sheet up here. I went ahead and took out the part that said that you had to use DocHub. There was a bunch of confusion on that. You do not have to use DocHub to submit your work. It is strictly a good option for students who are either having trouble with printing and submitting, or students who are having trouble taking pictures, or whatever that issue may be. If you have a format that you've been using to submit your work that's been working, please don't feel the need to change anything. This is just a good option if you can't print anything. That being said, we are also taking one step back. We're only doing a single practice quizzes this week. The mastery quiz from the first week is still open. Again, I strongly recommend that you practice the homework and the practice quiz first before you do that one. There is a problem in there that can only be answered with the video, so that's from last week. Without further ado, let's jump into 6.2.4, and one of, if not the most important topics of this entire section, which is called combining like terms. Some of you have already been introduced to this, and I may have already inadvertently taught you some of that, which is fine, in which case it's going to be a pretty easy section. Your goal is to be able to write a complicated or challenging expression in a much simpler, cleaner manner. And I'm going to kind of show what that means. So we're going to look at just this first one, and it says to build the shape using algebra tiles and look carefully at the length of the sides. Now, these are already built for you, and I'm not going to ask you to redo these. So when you look at this first section right here and you are labeling the length of the sides, the thing to remember first of all is that if you have an x squared tile, okay, if the tile is an x squared, what that means is that along each edge the length is just x. So there are 4 sides that have x on them, but because we're dealing with perimeter, because we're dealing with perimeter, you should not plan on needing this side over here. You don't need that side over there in order to do stuff. So we're labeling these 4 sides. You've got x, 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 and then this side over here on the right is also an x, along with these 2 little sections top and bottom. Now, if you remember the bit about unit tiles, these lengths are 1 on each side, top and bottom. And so when you are asked to write the distance all the way around the shape, one way that you can do that is by writing x plus x plus x plus x plus 1 plus 1. And the issue is that this is clunky. It's messy. It's hard to see. So we're going to get into this idea of combining like terms, which will allow you to write this in a simpler fashion. Again, some of you already know this, and you may have inadvertently picked up on this. This is just a formal way of describing what's going on. So the first thing I'm going to do is I'm going to identify all of the x values that I'm working with. I've got 1, 2, 3, 4 x's, and they are all positive. I'm going to emphasize that the symbol in front of them has to be included. So you've got 4 x's there, and you write that as 4x because it is 4 copies of x. And you can consider this 4 times x if you would like. And then you are adding to that 1, 2. So the overall perimeter of this shape can be written as 4x plus 2, okay, because there's 4 all the way around the outside. Now, I'm going to take a look at this one because this one is also a little bit stranger. And it does require you to be a little bit tricky with how you go about doing this. So I'm going to label these in the same colors as best I can, where you notice this top part is a 1 unit, this top part is a 1 unit. Each of these 3 little sections are 1 units. And for sure, this full length on the left side is an X unit. So again, if you remember, those X tiles are 1 on the top, 1 on the edge, and then X along the long side. The big challenge now is, what is this length along this edge right here? Now, many people are tempted to call that a length X. However, it does not work as an X value, because this entire side, yes, the entire shape, is X units tall. And again, if you kind of see where I'm getting these numbers, these expressions, the entire shape is X units tall. It's the same length. However, it has a small chunk that has been removed from it. This little length right here. So the overall length, you don't know a value of X. You cannot approximate it and say that it looks like it's about 3 unit tiles or 4 unit tiles or 3.5 unit tiles. You cannot do that. But this entire length is an entire length that is X units long. And then after you have those X units, you are subtracting 1 unit off of that. So this section here, this green section that I labeled right here, has a length of X take away 1, or X minus 1 on there. So now I'm going to go back and I'm going to erase some of this extra so that we can more clearly see the rest of this. Okay, and I don't need this little length in here. Because now when I go to add up all of the sides, I'm going to start here with an X plus, now there is this X minus 1 expression. You write it as X plus, and then you put the X minus 1 here. It means the same thing. It's just X. This length is X minus 1. Plus, then there's 1, 2, 3, 4, 5 ones. 1, 2, 3, 4, 5 ones. And you see right away why the combining like terms is important, because this is not a pretty expression. So I'm going to go through, let's combine all of our x's. This is a 1x. This is also a positive 1x, which gives me a total length of 2x's. Again, I am emphasizing strongly that you have to include the symbols, because when I go to combine all of these, that is a bunch of positive 1's, which is 5, combined with this negative 1 right here. Negative 1 and 5 is positive 4. So this perimeter is written as 2x plus 4. Okay, it's written as just 2x plus 4. So you've got the distance around the entire shape that you're dealing with, and then you start simplifying it by combining like terms. Now, you can do this in any of these expressions, and you could even combine like terms ahead of time before you write out this horribly long expression, especially as these problems start getting more complicated. So I will leave part 3 up to you as an exercise, but I will tell you that this bottom side can be looked at the same way. This length is x, but it has a single unit chopped off of it. So these two lengths on the left and the right together have a combined value of x minus 1. You could also visualize taking this first shape right here and simply rotating it down here, and it looks the same value, where you've got a side that has a unit tile on it for one of these, and then this length in green is x minus 1 again. But it's the exact same expression as if you had taken the same exact algebra tile and slid this 1 unit around so that the x minus 1 is simply made up of these two parts. So you have this x minus 1 expression when something has been subtracted or taken away from it. So that being said, let's look back at the rest of this lesson. They do ask that you color code links that are the same. I strongly recommend that. Now, one of these vocabulary terms that's going to show up is called a coefficient. Now, a coefficient is pretty simple. It is a number that tells you how many of each variable you have. And if you recall, the x in this expression are called variables. So an x is a variable. An x squared is also a variable. And in this case, the coefficient of x squared is 3. Okay, the coefficient of x squared in this expression is 3. And if we match this to the picture that's here, okay, if we match this to the picture that's written here, where you have, there's 1, 2, 3 x squared expressions. So that's why they wrote 3 x squareds. And then they also wrote that there were 4 x values, 1, 2, 3, 4, plus the 4 x values. And then these unit tiles, 1, 2, 3, 4, 5, 6, those are called a constant. Okay, so you have coefficients, which tell you how many variables you have, and you also have constants, which tell you the unchanging amount or the number value that goes with this problem. I will say also that when you look at this with algebra tiles, if I asked you how many x tiles there are, it's very easy for you to identify that there are 4 of them. Because when you're looking at tiles, the x squared and the x tiles look very different. You need to understand that one of the common mistakes that happens here is that people will look at 3x squared and 4x, and when they go to combine like terms, they will assume that the 3x squared and the 4x can combine and make 7 of something. I often like to give this example to classes, although it's a little bit less funny when I'm doing it digitally. If I gave a student 5 apples, and I gave another student 3 watermelons, and then I asked you how many apples or what do they have? Like I gave a student 5 apples and then I gave them 3 watermelons. There are very, very few of you, short of the most smart aleck students, who are going to say, well, you have 8 watermelons. That doesn't make any sense. You cannot combine 5 apples and 3 watermelons and all of a sudden you have 8 apple watermelons or 8 water apples melons or something equally silly. It's the exact same concept when you are dealing with like terms. If I gave you 5 x squared tiles and then I also gave you 3 x tiles, again, using this same concept, 5 apples are very different than 3 watermelons. You cannot combine those and say, oh, I've got 8 mutated apple watermelon fruits. Just like when you're doing this, if you have an x squared term and an x term, those cannot combine. Okay, this is an expression that is done being combined. So that's my big spiel on combining like terms. Now, I'm going to jump into a little bit of homework help here, but I will remind you that this math note section is fantastic. They walk you through a bunch of things on how you do this. And I'm going to show you one example of how you can combine like terms, especially when you are doing this on a piece of paper and you don't necessarily have a whole bunch of different colors available to you. So I'm going to do this all entirely in one font color. A trick that I have seen is that you can draw different shapes around different types of expressions. So 2x squared, and then you look through this expression and you find any other x squared expressions. Again, I'm keeping the plus signs in there. It's important. When I combine these, I say, well, you have 2x squared tiles, and then you have another x squared tile. Brief note, even though there's no coefficient written here, this is always imagined as a single x squared. Even though there's no coefficient there, it's written, you can pretend there's a 1 there. So when I combine these, 2x squared plus 1x squared is 3x squared tiles. Okay. Also make note that the exponent above that does not change, and do not say 3x2. It's not correct to say it that way. This specifically is 3x squared. Now I look also and I say, oh, well, how many x's are there? This is a positive x tile, which again you can think of as a positive 1x tile. And then there is also a positive 5x tile. Positive 1 with positive 5 makes positive 6x tiles. And then you can look at the whole numbers. So positive 3 and positive 2 combine to make a positive 5. Again, you are just adding these things up or subtracting. I just didn't want to get too much into the adding subtracting part of it. Okay. And again, in example 2 on this problem, I can say, well, here is a 3x squared tile, a 3x squared. A like term to that is this negative 2x squared or a minus 2x squared. The reason why you have to include those symbols is a lot of people will see this and just say, oh, 3, 2, I have 5x squared. That's not correct. 3x squared minus 2x squared leaves you with a 1x squared. But whenever you have a 1, you can just represent it as a x squared by itself. You do not have to write the 1. I found, however, that it helps, especially when you're first starting these. And then I look at the x tiles. I have a positive 2x, take away 1x. Again, pretend that that 1 is there. 2 minus 1 is 1x. Plus 1x. And then a positive 7 and a positive 7 makes positive 14. Okay. So that's just kind of a brief review of those combining like terms. I will jump into a couple of homework questions on this. On each of these, you're going to do both perimeter and you are going to do area of these. Let me open up the actual assignment so that I can show you what this looks like. So you're going to do both perimeter and area of these shapes. Again, in part B, you're going to have another situation where you have a bottom segment here that is x minus 1 on the tile. 6-107 is combining like terms. You do not have to sketch these if you're submitting it digitally. Just tell me how many x squareds, etc. there are. 6-108 is a little bit different than the book's description. I want you to represent these in 2 other ways. If they're a mixed number, you can represent it as a improper fraction, a decimal value, a percentage, or you can write it in words. For example, 1 2/3, or when you turn it into a decimal, it gives you 1.66 repeating, so you could do it that way. On 6-109, this is another way to think of changing these things to improper fractions. So when it says how many eighths are there in 5 5/8, 5 is the same thing as 5 copies of 8/8. So 5 5/8 can be thought of as, well, 5 is the same as 5 copies of 1, which is 5 copies of 8/8, which is 40/8. plus the 5 over 8 is 45 over 8. But nobody's going to do it this way. You're going to continue to use the same tricks that you've been doing, where if I want to convert this to a mixed number, or from a mixed number to an improper fraction, I multiply 8 times 5 to get 40, which, surprise, surprise, is exactly the same thing we had here, plus the 5 on the top, which gives me 45 over 8. All this is doing is asking you to write it as an improper fraction. Okay. On 6-110, when you go to evaluate an expression, use parentheses. So if I'm plugging in a value, j equals 4, I start with 6, parentheses where the letter j was, minus 3, and then I plug in that number 4. A couple of mistakes I saw recently. This is not 64. This is 6 times 4, which is 24 minus 3 to give you 1. On part B, you don't need the extra parentheses. You can just keep it as 3 times 3 plus 5. Again, it's not 33. It's not 3 plus 3. It's 3 times 3. So that concludes the section 6.2.4. Sorry this video ran very long. This is a pretty important topic. Hopefully the next ones will be shorter. Good luck.